Good evening. Before we begin, I would like to ask you to observe a minute of silence in memory of Igor Krichyver, who died last week and who was a brilliant mathematician and remarkable man. Okay, thank you. Now I introduce our today's speaker, Professor Valentin Lychagin. He will tell us about invariance of differential operators.
Yeah.
Okay.
Относить с собой?
Это карман можно положить, а это куда-нибудь. За пазуху. Главное, что тут какая-то защита. Okay.
So, good evening. I will present maybe the final lecture on invariance of differential operators and as a byproduct about classification, at least local, of differential operators. I presented few talks on this topic in this seminar, so hopefully it will be the last one. So what I plan to talk? We will consider two types of operators. The first one, it will be linear operators. So in coordinates, something like this. Operators of the order k on some manifold, so this x coordinates, so it's x1, xn. So obviously the diffeomorphism group, so if it's on manifold n, then we'll consider denote like this. It's third group of local diffeomorphisms of n. So it's obviously act of this on the space of such linear operators. And the question, first, it's about invariance. I will call this invariance natural invariance, in the sense that it's invariance of this group of diffeomorphisms. And the second, what about local or global equivalence? It's the first problem, and the second, very close to this one, will be non-linear differential operators. So they are very similar to this one. So I will write like this. Okay, it's a small sum of this in sigma x q d sigma, and also the sigma. So U is reserved for our function. So action of this operator on the functions, it will be, we should put f here, function f and f here. So it's just reserved notation for this. And then this operator will be, this type of operators will be non-linear. The only I will add some requirements on these coefficients. So if you fix, so first let's take, say, rational functions in U and take some finite extension of this field. I will use something like this, F. And when these coefficients, if you fix X, is elements in U are elements of this field, then I will call this F nonlinear equation. For example, you can consider U, but you can consider something like square root of U or U square plus square root of U and so on. So it means that they should be algebraic functions in U. Once more, the diffeomorphism group acts on the space of such operators. So, and we, like in the previous one, interested in natural invariance. So invariance of this operator that invariant of this group, Taylor group of local diffeomorphisms, and second, about local equivalence. You will see that this locally linear, not why I put this commas, it's in reality, it's a way to, if you will use this local to construct charts on manifolds, you will get the global equivalence. Okay, so this is my goal. I will start with the linear case, and after I will tell a little about this nonlinear case. Really, this type of problems I considered here many times. So the first, it's when k equal to, maybe this is the best case. It's more elaborated than all others. And say n bigger than 2. So this linear operators of second order. And what we know about them, that there is if the symbol of them not degenerated, we have Levi-Civita connection. Using this Levi-Civita connection, you can split this operator in the sum of operators that corresponds to each order. So symbol operator, sub-symbol, and so on. And then it means that this classification is simply classification about some sequence of symmetric tensors, something like this. And it's after this, it's very easy to find all invariants. It's what was done before. If k more than 2, say 3 or more, we know only the case n equal 2, so on the plane, and also not too much. We know only equals 3, k equals 4, and that's all. The cases when, say, k more than 2 and n more than 3, at least it was case that I simply afraid to touch. It sounds very, very, very complicated. The only that I'm sorry, I forgot to say that all that I will present here is just our joint research with Valery Yamaguzhin. So, so all this, it was done in something by hands, but this case, we did only for the case when symbol of this operator, it will be some symmetric k degree tensors, and we simply have very poor knowledge about their structure with respect to GL group. And it was really a crucial point that we did not succeed in this. Okay, and the way to pass from linear case to nonlinear case, I presented it for this case and for this case. It was just more or less straightforward. Okay, so but now I will remove this previous history of this problem, and we'll talk about case when k will be more than 3. So I will remove the case of differential operators of order 2 when I said it's more or less easy to do because of this Levi-Civita connection. If you will consider differential operators of the 3, 4, and so on, we will lose this option. So at least I don't know any reasonable connections in such situations. And I will change my mind, and instead of attempt to find such connections and split differential operators in sum of symbols, I will do slightly different way. So first of all, let's use these notations. So this will be sometimes it will be modulo differential operators of case of order k, but just in this moment it will be bundle over manifold M of such that section of this bundle will be differential operators of case order.
Linear.
Or linear, yeah. It's about this case, it's a linear, yeah. So there is this well-known exact sequence of these bundles. So k minus 1 is just part of operators for the less or equal k. And this map is just symbol. You take operator and take symbol, where you will get this tensor. So this symbol map. And what this sequence tell us? First of all, when we talk about invariance, yeah, every time I will mean differential invariance. So it means that, say, I will take this bundle. Okay, let's do the same. Like k. And consider jets of sections of this bundle is the same that I will consider jets of differential operators. This is group observer group X on this bundle, so it X on jets of this bundle, and we can ask about orbits of this action on this bundle. Now, action of this group on the manifold is transitive, so it means that we can consider, so all invariants you can calculate in one point, and after by translations just expand on all manifolds. So we'll take some base point here, B, and take jets and this at this point B. So this means that jets of operators at the point B. It's just vector space. Dimension, if I remember, n plus k. This action will act here by jets. What is it? K plus L jets of diffeomorphism preserve point V. anyway, this is some good group. It's implicit algebraic group. This is vector space, and we have action of algebraic group on this space. And the question about invariance and simply questions about invariance of action of algebraic group on the vector space. So there are two ways of consider such problems in algebra. They like very much Hilbert theorem and try to find invariant polynomials, compute dimensions, how many polynomials we have in each order. Unfortunately, or maybe fortunately, it doesn't work for group GL. Because if you take, say, simply action of group GL on vector space, then 100% sure that the invariance will be rational functions, but not polynomials. So there is a Rosenlich theorem that this theorem said that if you want to describe orbits of this action on this space, we should restrict ourselves by rational only invariance, rational functions. Then these rational functions form some vector field, sorry, some field without vectors. And what we know about this field, that this, first of all, this field will have transcendence degree equal codimensions of regular orbits. It's more or less, it's not obvious really, but in classical mathematics, they said that we count constants. It's like computer codimensions. And it means that if you, and this field, by the main point that this field will separate regular orbits. So this is exactly the set of invariants that we will try to find. So once more, so this rational invariance here, I will call L or natural L invariance. Just to the full title, you should say a natural invariance of the L, or less or equal L. So this is the problem that it's now very far from geometry on the one hand.
Which invariants are unnatural?
Aren't
they natural by definition?
No, unnatural, it just takes, say, rotation group or symplectic group. It will be symplectic invariance.
But we can see the group of different.
This is natural because of this group of diffeomorphisms. In physics, they call that physical laws should be natural when they say that they should be independent on laps, or in other words, independent on choice of coordinates, or in other words, they should be invariant under the loop. Okay, it's not my job. Okay, so this is the first problem. It's on the one hand, it's very simple form. We have a vector space with a group that you can explain directly. So possibly it's very easy to find this field of invariance. Unfortunately, it's too brave statement. So we just will try to understand what we can say about really this invariance. And the first remark, and at least for me, it sounds maybe very silly, but for me, the first remark that from this sequence, it follows that if I take invariance, not differential operators, but invariance of these tensors, invariance of symbols. And then if I take invariance of symbols, just because of this sequence, I can put them on this place by taking symbol B star. So I will get invariance of differential operators. So simply saying it just means that instead of computing differential invariance of differential operators, we will try to compute differential operators, differential invariance of symbols, and they will be just not all, but it will be part of differential invariance for differential operators. Okay, it's easy to say, but not easy to do. Now let's say about this. So first of all, these symbols, they are simply at the point B, they are simply homogeneous polynomials of degree k on cotangent space, right? It's the first one. Now, what we will get from this action? So on these tensors, it will be simply G, L, and action. So now my critics. It's a classical problem to computing so-called N forms or GL classification of N area forms. And now this is a classical problem. I don't know, is it 2 centuries or 3 centuries problem, something like this. Say for n equal 2, it's the problem that was really origin of invariant theory in, I think it was in 19th century. When I first touched to this problem, it was a surprise for me that still we have no idea about invariance, not GL, but SL invariance on the case of n equal 2. At least experts in algebra, I think that now not everything, but some facts known for k equal, I think something up to 11, something like this.
For a cell?
For a cell, yeah, for a cell. So what is cell 2? So this is what really point where I simply gave up and stopped to think in this direction, because if it's difficult to say for this simplest case, what we can say for n bigger than 2. Okay, so now let's discuss a little more about this problem. So we have simply, okay, I forgot really now all this geometry, and say we have n-dimensional vector space. So this dimension of this space for n, we consider these guys as a homogeneous polynomials of degree k on V. And we have action of group GL on this space. So the question, what we can say about invariance of this action? Do we able to find some invariance or not? And by the way, it's I forgot to say this. Yosef, you showed me this Geometry 1 book. This is one author of this. And at least in these books, I think it's more or less known. But in these books, it was written very clear. There is so-called principle of n invariance. It's not universal principle, but for us it will be very important. We will see that to solve this problem, we need not all invariants. Really, we need only n of them in general position, and then we can find the rest. So all invariants can be found just simply by computing, by using only n invariants. So it means that for this section, also I will not interested in all possible invariants of this action. I'm interested in a very primitive question. Do we able to find n invariants, certainly independent? Okay, so let's take n equal 2. And let's run. So I escape. I will never use it case when k equal 2 here. So let's take k equal 2, k equal 3. So this is it's 4-dimensional space. Our group GL has also dimension 4, and it's easy to see that in general polynomial of degree 3 has no stabilizer. So it means the dimension of orbits should be 4 minus 4. It means 0, and really we have this quotient. It's just so we have no invariance in this situation at all. If you have the next case, so dimension 5 minus 4, it will be just only one invariant we hope to get here. So it means that for dimension 4, for order 4, one GL invariant for symbols we can find, and we can use it here, but it's not really true for this case. So S5 of V star, it's can be computed yet, the dimension or dimension of orbits will be 2. So we have some lucky case. So in this case, we can use it only these 2 invariants to find this 2 invariants. Is it enough to find all invariants of such type of operators? So the next will be 3 and so on. So the question, how to find invariance here? What we know from elementary algebra. So how to find invariance of polynomials? I think practically everybody knows one invariant, namely discriminant. It's for sure invariant. But discriminants, it's only one choice or one candidate for invariance, but say how to find, say, 2 invariants or by the way, discriminant, it's not invariant of GL, it's invariant of SL. So simply here to find SL invariance, we need 2 invariants in SL. So discriminant is given only 1 invariant. So the question could be find the second one. Okay. Now I will leave algebra and will return to calculus. So say we want to find SL invariance on this SK vista. First of all, SL it means that we have some volume form on this space, invariant volume form. Invariant volume form, I will take not form, I take dual to this invariant volume n vector. So it will be in basis something like this. So this means that the guy is invariant of our selection. Now, instead of this vector, I will consider his origin. So I will take a vector that present to our omega. It's up to coefficients, it's the same. And so what? It's certainly vectors, but I will change my mind. Instead of vectors, I will write derivatives or vector fields that corresponds, constant vector fields on the space that corresponds to this vector. Then this omega will be now not this, but this guy. So where this guy acts, let's take beautiful F. It simply functions on the space V. It can be say something like this. Really, I mean polynomials, maybe homogeneous, maybe not, but just for this business, it's no need to have some conditions that they are polynomials. So then this operator, so all these tensors is over R. So I will consider this guy as operator that act in F tensor degree n to F tensor degree n. In just an obvious way. So if you take something like F1 Fn, then it goes like this. You should apply d sigma 1 to F1 and tensor d sigma n Fn, take the sum and sigma and minus 1 and degree sigma here, just like this. So I apply this operator to functions. In some sense, functions on some degree of V, but we will consider like this, so on the objects like this. So what? The only that we can see from this construction that this operator is SL invariant.
Well, why are you now speaking about SL invariance? Which part is
It's because you see, GL in this situation has no polynomial as invariance.
no polynomial.
Yeah, but SL they have polynomial invariance, so it's much easier to find them. And but GL invariance is simply ratios of SL invariance. So this is why I play this is SL. So for practical needs, it's better to use SL. But for our needs, we really need GL. But the difference simply, if you know SL, then you can take ratio and you get GL. Okay, so now I will introduce some bracket.
SL invariance means that you F by SL on V,
Yeah,
and then
and
it
lift,
generates
yeah,
this
yeah, yeah. So we have the following situation. So we have, say, n functions. Then this from this f functions, I will take the tensor product. So I repeat the tensor product over R. Now I will take this operator and apply to, so let it be simply F. So I will get this guy. But this will be just, as we know, it will be just once more in tensor degree in this space. So functions, tensors, operator, element here. And what I will do after all, I will take multiplication. So I will take multiplication from this to F. Take result and multiply. So what I will get, I will denote it like this. F1, Fn, and here. I'm sorry. I will take not this operator, I will take some power of this operator. And then it will be, you can take L equal 1, then we will get what we had. But if you take power, you will get more really options here. Okay.
Will it be 0?
Why? I just, okay, let's. No. And equal to. So what is our omega? It's d1 tensor d2 minus d2 tensor d1.
D, yes. Yes, of course not.
So when you when you take this bracket,
Yeah, of course.
it will be possible. So if you take here the same, it will be simply Jacobian of n functions. So this is why I just said that I will take some A. Certainly, if L equal 1, and if these functions dependent, so there are some relation between them, then certainly you'll get 0. But in general, we will just Jacobian. But when L is not equal 1, then we have something more interesting. So I am sorry, I should use my, how they call this? Okay, my notes just to. I forgot this English name for this. Yeah. Transfer stance.
This bracket is called.
Yeah, they call this. I only know that for n equal 2, this expression coincides what they called in standard literature. Is it the same for different n's and l's? I am not sure, but it's easy to find, but Now it should take d minus 1. Yeah, d f1 dx1 in degree e. No, L minus e. А? Как?
Смотри. У нас все в порядке. Давайте я включу. Скажи что-нибудь.
Мне сказали?
Ну да, у тебя же.
Да. Появился, да? Okay, so for dimension 2, we have explicit formula for this. Really, I have explicit formula for this also, but it's very long. I can show you. In this case, it will be x2 in degree I and multiply on this. So when L equal 1, you will get exactly exact Poisson bracket, but as you see that for all other. Anyway, it means that if I take, say for this case, if I take two functions, two functions that in some sense invariantly are related to my function f, say for example invariance, some invariance, then this bracket give me once more also invariant. So the easiest function that invariantly related to f, it can be f itself. What we can see from this formula that this is if L odd, then this is skew symmetric expression. So for L equal 1, it's simply Poisson and squares. But if L even, it's simply symmetric. So it means that if I take this bracket, but take say L equal 2, then it will be something but not zero. Say I'm interested in invariance for polynomial of degree 4. Then I will take this bracket. Okay, it's silly to take, say, bracket with label 1 or 3. And also with the label, say, 5 and so on, because it's the derivatives of order higher than this polynomial. So, but this guy, it certainly will be invariant. Now let's see what this guy tell us. First of all, it's a quadratic expression in coefficients, so it's because it's quadratic in P. So this invariant, but invariant of second order in P. But the second, what is more important, when you compute this is derivatives will be simply constants. So this will be constant. So this is really invariant. And it's true for all even degree polynomials. So if they say take polynomial of degree, say
Why it is constant?
huh?
Why it is constant?
Because when you compute this,
Ah.
the derivative exactly of the 4 and this is 4, so then you'll be constant. So clear, right? But if I take also some non-trivial expression like 2, what I will get? Yeah, I differentiate 2 times and multiply on derivative of 2 times. And after just sum it. So, but this is 4, degree 4. Then it will be degree 2. This degree 2. When I will multiply, I will get a new polynomial of degree 4. So from given polynomial of degree 4, I got for nothing polynomial of degree 4. And this relation is L invariant. So when you just move this guy by SL transformation, this will be just automatically moved by SL transformation. But this is once more polynomial of degree 4. So I will take now bracket between them. With degree 4. This will be now once more invariant. This invariant was degree in P. It was degree 2. This will be in degree 4. So this invariant of degree 4, 2, and this invariant of degree 4. Now, what about discriminant? So this is polynomials of degree 4. So the discriminant should be 4 plus 4 minus 2. It should be degree 6. So this is two invariants that we found, and once more for nothing. But this invariance low degree than discriminant. I did some very simple computation, so I hope that.
So this is 2, this is 4, and discriminant is 6, yes?
Discriminant 6, yeah. So what we found is really it's easy to check that discriminant really will be it should this is degree 2, so it should take cube of this, and I think and some product of okay. So it's discriminant just combination of these two. Sorry, I have really very simple. This is the only case that I will give you simply concrete answers. So if you have polynomials like P4 x4 plus 4p3 x cubed y plus 6x p2 x square y square plus 4p1 x y cube plus p0 y4. So let's write our polynomial p is this one. Then the first, so let's call this invariant of G2, and this is invariant of G4. Then G2, by the way, I never thought that we can get invariant of degree 2 in this so complicated problem. So it will be the following guy. P0, P4 minus 4, P1, P3 plus 3, P2 square. Up to multiply because I removed some big coefficients. So this maybe multiplied on something, but for invariant it was not important. So this guy, and for me it looks brilliant. So the next it's G4. It's a little longer. It's P0, P2, P4. Why I say I was wrong really. It's not. Right. We have really something that it has third degree, so it will be. Certainly, we can play with this game and construct a lot of invariants, but remember that we need really few of them. So for the dimension case, we need only 2. So minus P0, P3 square minus P2 P1, sorry, P1 on P3, no, P4 square plus 2 P1, P2, P3 and minus P3 square. So what wanted to show you that really this is not so, yeah. Unfortunately, Mitya, when he taught me mathematics at school, he never taught me about such beautiful constructions. Okay. And it's easy to see what happens when you take this as brackets for homogeneous polynomials, because first of all, you differentiate L times. So it means that degree will be dropped on L. And after you take their product, so you can compute what is the degree of these polynomials that you will get after this manipulation.
And they are always homogeneous, yes?
Really, this works simply for any functions. But for homogeneous polynomials, why we use them? Because we keep. No. For this construction, just F1 and F1, F2, it's just simply functions. Also. It's just simply functions. You see, we go to these constructions, we never cares about how complicated this F.
Yeah, of course, but if you start from homogeneous polynomial,
you will get homogeneous. Yeah.
Excuse me, can I make a comment? Valentin is Женя Ferapontov.
Да, Женя.
Okay, so these two, I forgot, are we talking in English or in Russian? Your talk was in English?
Yes, in English.
Ну, я понимаю.
Right, sorry. Okay, so these two invariants, G2 and G3, they have geometric meaning. So what G2 means? So your polynomial, it has 4 roots, right? And these roots have cross ratio. So this cross ratio is GL2 invariant, right?
Yeah.
And
you're completely right. All these brackets can be computed in terms of roots. Yeah, I agree with you.
Yeah. No, but they G2 and G3, they have a meaning. What G3 equals 0 means the cross ratio is -1. They're called harmonic.
Mm-hmm.
And G2 equals 0 is also a very special value for cross ratio.
Okay.
So in terms of cross ratio, these are known expressions. There are two specific values for cross ratio, because if you take cross ratio and change the order of roots, you have several values for this cross ratio. So something like 6 in general. But in some cases, the number of these values decreases, and these are precisely G2 and G3. So these are kind of known interpretations.
Oh, yeah, Zhenya, thank you very much. But for me, important that they are very simple and it's very easy to find them.
Okay.
It's just because I am interested in invariance of my symbols, and such expressions, it's really easy to, it's not just some too complicated theory to find this invariance. Yeah, so but what I want to say is that in one invariance, GL invariant for this problem in degree 4, it will be this one, G3 and square divided by G2 cube. It's obvious, right? And by the way, about discriminant, so discrim is the following. It's G2 in cube minus, sorry for this numbers, 6, 9, 12, G2 in cube, G3 in square. And by the way, these conditions for polynomials to have multiple roots. So if this invariant is really invariant,
So you state this
This is-
A is
it's GL2 G2 invariant, yeah.
Is it obvious?
Yeah, because this is quadratic coefficients, this is cubic coefficient. So if you take this ratio, you will get something that will not change
Yeah,
at the
yeah.
multiplications.
Mhm.
Okay. So what I wanted to say is that using all this is construction, at least for dimension 2, it helped you to find invariance. Really, I never check myself. It's historical historics in mathematics. They claim that Boole proved that all invariants of binary forms can be found by using all these brackets. And now the computations of invariance is not just some problem, because you simply should take possible brackets and try to remove the degree, to reduce degrees result to the zero, like here. And this gives a Milk invariant. Okay, I tested myself and take this case when k equal 5. It's not so easy, because after A will be afraid to touch polynomials of degree 5. But so it means that to take, say, this type of bracket, it's nothing interesting, it's 0. So this also 0. And this also 0. So the only two interesting invariants in this one and this one. So this has degree 5 minus 2, 5 minus 2, it's 6. And this has degree 2. So at least this gives us immediately one invariant. So because this has degree 2, so we can take discriminant of this. But discriminant of this guy, it's simply this one. This degree 2, this degree 2. So if you take this bracket with this label 2, then you will get some constant, and this will be just invariant. So one invariant we got immediately, and the second one, it's also you can play another game. You can take P and bracket P and P. So this is degree 5, and this is okay. What are say 4?
Orders,
So this is
the second bracket. Which order?
this order 4.
Yes, and
Even this, yeah, the second you can easily see. So this degree 5, and this is degree 2. So the order that you can take degree 2, this here. But it's not big success, because it gives us some polynomial of degree 3. So it's some game with brackets. So you can play different types of brackets and see when you will get this invariance. By the way, you can get immediately invariant. Take not p but p square, then you will get polynomials of degree 10. It's even degree. So this gives you invariant immediately. The only that it's why it's not so good, because it will be
How can you be sure that they are independent? Well, you generate, but
yes, so, yeah. So certainly you finally when you will
you need to check.
yeah, every time you should check it. Do they dependent or not? But when we just will back to our differential invariance, it's very easy to find, because it will be functions on jets. You should take the total degree, differential, take product, and if it's zero, then it's not the case. Okay. So
I'm speaking of algebraic.
yeah, you talk not only about it, but when I just remember this sequence. So if you find invariance of symbols, so if you have operators of order 5, take the symbol, take invariance of the symbol, but we need here not 2, we need here 3 really invariance, because 2, because this is GL SL invariance. So to get GL, we should take ratio. So we need 3 invariants to get 2 in GL invariance. So this is I play with this, so it can be done. What I wanted to say that first of all, this is just some toy that you can play with this and construct this invariance. And if you believe in this theorem that all invariants can be obtained simply in this game, then it's the way to find, at least for dimension 2, it's a way to find all algebraic invariants of symbols, and therefore all 0 order differential invariants for differential operators. Okay. I also prepared something in the first non-trivial case. It's about n equals 3. K equals 3. It's a famous case. It's cubics on 3-dimensional space, and the interesting in G have 3 invariants of this, or orbits of this action. As far as I know, first who tried to attack this problem, it was Amy Noether. He found a lot of really invariants, but she was not sure that she found all of them. So I never saw this paper. It's only once more just in literature. I saw this statement. I am not sure that she used this brackets. In this case, it should be brackets of 3 functions. Of some level L. So once more, you can compute degrees. As before, you should try to, so because we have our polynomial, so the first, it's just you can simply take P and P, but once more, when L will be odd, we will get 0. But if you say take some P square, and take the bracket for the 6, you will get immediately invariant. Maybe it's not the more simple one, because it's certainly in coefficients of P, it will be degree 6. So I don't think it's a good idea. Okay, but I don't want really to spend more time for it. It's just very simple game to find invariances. Really, once more, you have here only one. You can compute this only. You're looking only for one GL invariant. This codimensions of GL orbits will be one, and so it means that you have only one invariant. In other case, you should try to find two SL invariants to get one GL invariance. So the more stupid picture, just take this ones. So this is certainly two invariants. But first of all, you should check that when you take a ratio, you will get something not trivial, because if it's simply. But anyway, it's ratio of two polynomials. No, I think these ratios can be just ratio of these two SLs with some degrees can get you some invariant. But there are another. Okay, I don't want to talk about it. Anyway, it's really my favorite topic, really, to find answers on the questions in invariant theory, in algebraic invariant theory. The best way is to go in geometry. Then you will get some really tools or devices that will help you to do this. Okay. Anyway, it's the one way of getting invariance zero order for differential operators. So this is what I have. This is and here symbol, and here this one. So when we found invariance here, we immediately will get invariance here. But we found here algebraic invariance, so it will be algebraic invariance here. So it will be zero order, differential zero order invariance of this. It's the first, and the second. If you remember, we discussed this when we take not arbitrary case, but when some case say equal 2 or k equal 3 that we elaborated, then we used such universal differential operators of also ordered k. It's act from C infinite G infinite of tau of ck. So this is bundle ck, and this is bundle ck minus 1. So this operator that acts on infinite jets of this bundle, of sections of this bundle, and this is operator also order k. And if you will write this operator in the form then and as a coordinates in this is in bundle ck, you can take functions u sigma, they simply computed coefficients in our polynomials, and this is in this jet coordinates, it will be a very simple expression. So it's simply you should choose this for total derivatives and this for universal coordinates of sigma. So this is this operator here. What is important about this operator?
C infinity or something is sections or functions? Functions.
Oh yeah, I mean that is it's an infinite dimensional space, so manifold, and this is one smooth function. So
So these are total derivatives.
Yeah, it's not okay. It should be. So this is the right formula for this. What is important about this? It's some universal construction in jets. So delta is natural in the sense that it's invariant of diffeomorphism group. So if you take transformation of your manifold, it's induced automorphism of this bundle, and therefore automorphisms of jet bundles, and this action, this operator commutes with this action. What kind of information we can gain from this operator? First, if I is natural invariant, this is GM invariant, then delta I also natural, also natural invariant. And so if this invariant has, say, order L, then this will be invariant of order L plus K. We just, because we jumped this. How you can use it, this? First of all, if you know some algebraic invariance of symbols, they are just invariant, so you can apply operator to them, and you will get K order differential invariance.
No, but you cannot apply it to.
Why?
Because
Take L equals 0. Invariance that we discussed before, it was algebraic. It means that
your invariant leaves in functions on the right bundle.
okay, take now this. I said it before when I said that invariant here give us invariant there. Yeah, so it's no. It means that all these constructions, say what just we discussed, say, invariance of differential operators of first order. So when this k equal 4, we have one this invariance. Remember this ratio. This is G. It's invariant of symbols or invariance of 0 order. So apply D to this. You will get an invariance of order 4. And this is order 0. This probability 100%, they're independent. In the case that D hat G, which D hat double G, it's non-zero on the open and dense set. It just will be complement to some algebraic. Okay, so it means that for this case, we have two differential invariants. Now we can apply, so this is E1, E2, this is two invariants. And so we can use them just to find our operator, really all invariants of our operator. So what I will do, I will take this operator universal delta and apply for degrees of this E. So E in degree, say alpha. So alpha, it's alpha 1, alpha 2, and length of this alpha less or equal. It follows that from the following very simple observation. To find these coefficients, you should simply apply the operator to all polynomials x, degree up to 4. Then you will get all this coefficient. And this statement is very similar. So if you have your operator, so take this invariance and compute on this operator. if this in general position, you can think them as a coordinates now. Then to find these coefficients A in these coordinates, you simply should take these guys and once more compute on your operator. So it means that these functions completely described coefficients of our operator if you use this invariance as a coordinates, value of this invariance on our operator as a coordinates on the manifold. And now what we can say, yeah, we have this, let's call this say G. So we have these two invariants, and this is invariance G alpha. So this invariance that I'm sorry, we have for nothing really. So just no computations we needed. And but what it means that you know this your operator and all coefficients of your operator in this basis, in these coordinates. Then it means that to find all differential invariants, how we can find differential invariants? We take these coefficients and start to differentiate this and see when we will get some invariant expressions. So we should take these as guides and differentiate in this, but it should be not usual derivative, it should be tricep derivatives. So if you take G alpha by dE, so all these possible derivatives, all orders, they give us simply all invariants of our operator.
I don't understand why all.
Okay, invariant of this is a function that depends on coefficients of our operator and derivatives. So derivatives, this is this kind of derivatives. So if I take these operators and this is derivatives, then all other differential invariants will be simply functions of them. And in the case when it requires rationality, you should say that all this ration, this ration.
Yes, but it is true if you start with, so to say, with a complete set of invariants.
This is complete set.
Why? Because a complete set for some algebraic action.
No. I simply take this operator.
Yes.
I want to find a differential invariance of this operator.
Yes.
What is a differential invariant? Is a function that depends on coefficients of the operator and derivatives of this coefficient.
Yes.
And this function should be invariant under
Yes.
derivatives. Now, instead of this, I will take which one? Yeah. G alpha by this invariance. Yeah. So if now I will take my operator and restrict these i's and these j's on this operator, let's compute values of this invariance on this operator. This will be simply some coordinates because of this condition. Because of this condition. But it's equal 0, it's simply give algebraic manifold in jets. So it means that non-zero, it means the risky open set, really. So it's true, right? Now, these coefficients, the restriction on equations give us exactly these coefficients. The derivative of these coefficients is the same that tricep derivatives of these guys by these guys. So it means that by definition, all invariants will be simply functions of this, and they will be invariant because everything here invariants.
Can you give some simple examples?
Simple. No, you should ask Valera about this. No, we published, Valera put it in archive paper about third order differential operators, and he gave some examples there. So it's easy to say, but certainly if you just take some operator and stuff, at least all of them, it's very easy to compute, at least with computer. because it's very constructive. And so now the question, so it's not important that n equals 2. It's what is important is how many invariants you're able to find using a symbol and invariance of symbol. And also this observation that if you take this guys from symbol algebraics, then apply this square operator, you will get one small operator. So you can add them to this i's and use this as a basic invariance. After apply these constructions, you will get this GA-alpha invariance, and they give you complete description of invariance now. What I want to say is that really, say if you have k bigger than n, equal than n, then sometimes you need only one invariant algebraic invariant to construct all invariants. Is it clear? Simply you can take this a single one and apply this operator to this invariant, to square, to cube, and up to degree n. And up to degree n, they will be independent. If you take a degree higher than k, we know that the commutation rule with the equation operator multiplication by functions. So we will not get anything new. Okay. So this is what I want to say about linear. Huh?
Well, what is amazing that to find GL invariants, you solve at first glance the more difficult problem finding a cell invariant.
Yeah, completely. Yeah, right.
Which actually is simpler than
difficult to say. It's simple. By the way, solving of this problem for GL for NR forms, it's still just I don't know, but I think that's algebraists, they simply afraid to touch this problem. Because for them, not the question to find few invariants. For them, questions to find all invariants, to find the generators in polynomial algebra of this invariants and etc. So it's what I tell you about this dimension 11 for binary forms.
That's all.
If you don't want to follow nonlinear case.
Oh yes, we do. I forgot about it.
Yeah, it's also not. I think I told about this really.
Yes.
It's idea also very transparent. So idea of this, so how we described nonlinear operator here. So f goes that you should take this sum sigma x f and how this derivatives of f. So this will be just certainly non-linear expression, but it's not certainly it's not arbitrary non-linear. Not quasi. Usually they mean quasi if it's non-linear in all derivatives. Yeah, it's more strong condition than simply quasi. But the problem that instead of manifold M, we take manifold of 0 jets of M. So this simply M cross R. So here we have coordinate X and this is coordinate Q. So this is coordinates in this space. And this is A, this operator A. It's a differential operator, linear differential operator of order K on this new manifold. In the form of like wrote here, like this. It's not arbitrary because there is no derivatives in Q here. So it means that this operator satisfies this property. It's commute with the multiplication by U. And by the way, I forgot to say that this is U. This is natural in the sense that it's invariant of this group GM. It's simply not invariant of differential operator, but it's invariant everything. So it's simply object that if you take G0 and if you take this is group of diffeomorphism and lift them to this space, it's zero prolongation, so you'll get something like this. So if you lift the diffeomorphism to zero level, because of this, you will get that U is simply invariant of this. Okay, so instead of this nonlinear expression, this nonlinear operator, I will consider this linear operator. So it's simply differential operators on the new space.
This will be different actually, not the one we.
Why different?
Because if you act on these operators in the initial form, there will be an reaction on U too, or not? Oh no, there will be
no, it is the same.
Sure. So you apply the action of this operator, you substitute F instead of U, yes?
Yeah.
And if you act on F's.
Yeah.
GF,
Yeah, but if you take this transformation and apply to a graph of F, you will get exactly action on the function.
on the graph, yes.
But it's corresponding action on the,
Yes,
but it's also action on the functions. No, this class of operators and this class of operators, this linear, they are related in an invariant way. So if you transform this operator by this phi 0, it's the same that it transforms this by phi.
Okay.
And this is, by the way, why only you present here, because if you take derivatives, it will be much more complicated picture. Okay, but in other words, instead of working with these nonlinear guys, I will consider these linear operators. It's on the new space, but who cares about this? Take this one and consider these differential operators. So let's call them. Oh yeah, I forgot. Later I will put here letter F, because remember that I tell that these functions, they should be algebraic in U, and this algebraicity means that this should belongs to field extension of rational function. This is F is field extension. Okay, so this is the only difference between the previous case. So not the only. It's one point that we should remember. And the second point is if you consider these operators as operators on this extended space on n plus one dimensional, they will be degenerated. We don't have here this GDEq and so on. So it's the degenerated operator. So in some sense, application of by the way, in the previous discussion, we never required that it will operator should be regular. So, but it follows from our constructions. We begin with a symbol, and for symbols we knew this invariance, but they certainly good. They separate orbits if you have regular orbit. So really, what we did with this invariance, we can use them only for symbols that belongs to regular orbits. So it means that all these previous constructions that we did, they will work only for case when our symbol belongs to regular GL orbit. And this is some kind of regularity. This operators, their symbol certainly doesn't belong to this. Anyway, what we will do? We will construct one more operator. And this is the following operator. I will take my operator, and instead of U, we'll get F here, and here we'll write like this sigma. So the only what I did, instead of this U, so in some sense, I restricted my operator A on the graph of function F. But this is now a differential operator of the K on the M, and assumes that we know everything about this. What it means we know differential invariance of this type of operator. So it means that we can find differential operator, differential invariant of this for this operator. So take some invariant here and apply this invariant on this operator AF.
For fixed F.
Well, yeah, for some fixed F, yeah. So what you will get, it will be some expression that depends on our coefficients A, their derivatives, and also derivatives of function F. When we will differentiate this, it will be derivatives of F. So it's not invariance that we're looking for, because in this setting, invariance that we're looking for, there should be constructions depending on our function A and coefficients A and their derivatives. There is no room for derivatives of functions. Okay, so how will this work? So we take our differential operators of the K on M, and so this is our bundle CK, and take K jets of them. It's where our invariance of this type live. After we have this new bundle, this is give, say also K, but G0, M, and F. And this is also, there is some bundle, but over G0. No, I mean just without F. I simply took.
Yes,
I will. F will repeat. So let it will be psi A with the tilde. So this is two bundles. So and invariance should be here. So it should be functions on the jets. Say K jets of this bundle. Okay, not F. Say L jets of this bundle. So, but this bundle here over M, and this over G0. So we have situations where we know invariance of GL action here, but we have no idea about invariance of this. So what I will do, I will use this constructions with IF, but what I will do, I will take over G0. I have also another bundle. Let's call this is PL0. It's of L. Okay, L doesn't matter. M. M0. It's jets of bundle of space of M jets of functions on M, but projections not on M, but projection on G0. So we have this is two, this is vector bundles, this vector bundle, this vector bundles. We have these two vector bundles over G0 of M. So then we will take, so this will be, say, psi y, k with the label L. And this will be psi k with the label L. So I will take the following Whitney sum. I will take psi tilde L and plus, it's also, we can play with this M, so it could be the M or any other. So, but let's do the pi M0.
You mean Whitney product?
Yeah. So this bundle, the only problem that we will have at the very beginning when we try to define invariance, you remember that we defined invariance here, we used the property that invariance action of our group transitive on M. Then we can pick one point and take all this construction only at this point. And this, at least this explains why differential invariance form a field. Because if you say that this function over all manifolds, then it will get some problem. What means, because at some points they can be zero or something like this. So, anyway, the way how we made this, we pick here this basic point, and everything we can compute it in this basic point, at this basic point, and everything was just very simple algebraically. In this case, we lose this transitivity because the diffeomorphisms, they did not act in transitive way over G0. So I will make the following. Yeah, but anyway, so this over G0. At least without this guy. It means that if I want to talk about field of invariance of this new differential operators, I should continue this bundle and consider this over M. So so this bundle psi tilde KL composition with the pi 0. So this will be just this our bundle project to M. So then in this bundle, certainly we can talk about the rational function and stuff like this. The only that behavior of all these constructions in the fiber of this, it's not fixed. And so this is why I need these conditions that coefficients, they are algebraically depends on U. So algebraicity or rationality in these fibers, I will formulate because I have vector spaces, but I will never get algebraicity or some kind of rationality in these fibers. So this means that in my operators, I should add either simply that these coefficients are rational in U, or more general, that belongs to some field of algebraic functions. Then we it's so then we can say that our differential invariants we require that they should be rational on this and rational in this way, but rationality here means that belongs to F. So then this invariance of GM invariance on this, it will be our invariance of these operators. Now let's see. We call this the bundle of related pairs because what is here? This elements in this bundle is K, L, J's, and the sum point X, U. And elements here, this is J's of some functions of M J's of some functions at point X. It's so the condition that this is pair from this and this should not should be, it is not arbitrary. So requirement will be the following, that f of x, this is our u. So this is requirement, and this is just put this two points together. And so this is we'll call related pair. So this is a pair jet operator, jet function, but with this condition, jet operator to the point x u and at this point x, and this is the relation between x. Yeah, and so now we have this map. So let's related pair. So related k, related ln. Yeah. So this is a total space for this bundle. And so we have a map from related space, related pairs to some jets over here. So J I think A or everything that's of CT. What is this? What is the map? I will take this pair. So this L at the point XU, and this is the point X. So this pair. And what I will do, I will take this construction AF, this one. So I take this operator AF. Okay, let's take L here, something like this. So L. Yeah, so say AF, but it's no need to differentiate F. So this will be just this one. So so this is map from this space to this space. So if I take invariant here and take image under this map, so I will have something invariant here, but it will be invariant. At least it will be G. So this construction is natural, so it's GM invariant construction. So this will GM invariant, and this will be GM invariant. The only problem that this invariant, if you compute, say, this invariant on this operator AF, as I said, the jets of functions F will be just a pair. But to get invariance of our operator, we should remove this is component that contains derivatives of function F from this invariance. How to do this? So let's once more. Let's take this space and take, say, functions, F rational functions on the space. Then it's certainly it will be some field, but in this element will belong to this field because it's rational, so it will be also rational. the only problem is how to remove derivatives of f from this guy. But derivatives of f means these components. So I should remove all of these components from this invariant. To do this, I just will define some derivation on this space. Namely, I have this derivation, it's vector field, du, vertical vector field, and u, it's also invariant, and this is invariant. So I have also this total derivative that is also invariant. So this is two derivations. One derivation x, so the first derivation, it's x here. Because this is the jets of this bundle over G0. And so GDE dy is this vector field here. And so I can take total derivative and
in this sense, U is independent.
Yeah. And this vector field, it's also invariant, but this act here. Because this is jets over M, and this is DDY, it's vertical field, so this is just point transformation of our zero jets, and we take prolongation of this. So this is derivation is something like this. So it should be functions of this guys on top of this much. So no, I take derivative on the. So functions on this, they tensor products of functions on 5. So this will say functions here, let's f, and functions here, let's g. So this is how the derivation act. It's Leibniz rule, but on f it's acted by this y, so it will be df dy du g plus, and on this it's act by this one. So du, what is the else prolongation on the g and multiply them. So this vector, this derivation on these guys. So it means that if I take this invariant I tilde, then I can take this invariant, I can take this invariant, etc. What is important from this construction? So this operator nabla, it doesn't lift this level of jets of our function. So if this invariant depends on derivatives of functions up to m, then all these operations will not increase the number of derivatives. This is the crucial really, because what I will do, I will take this as invariance. So this I0, let's see, okay. The first one, let's see, it's a derivative. It's the second, and etc. For any n. So this all of them are just simply functions. Yeah, but all of them contains derivative of this. But this field of functions, rational functions here, over this field, it's because it contains simply rational function on the G0. So it has transcendent degree equal to the dimension of this vector bundle. So it means that after some n, I will get simply algebraic relation between them. So I will get some polynomial of I0 in equals 0. This polynomial will be with coefficients from this side. And what I will say, okay, let's take this as the derivatives, blah, blah. And so all these polynomial relations between these invariants, it will be some ideal. Okay. Ideal G in polynomials in these n variables over functions. So this Q, it's from here, right? From here. But this is some field, and this is polynomial. So what we know that this ideals, they have basis. It's just they finally generate. So there is basis here. So let's say B1, BK. Okay. No, it's not field. It's polynomials. It's ideal in this
Not rational power.
This is rational functions, but this polynomial is coefficients in this field. Coefficients in this field. Yeah. And now what I see that everything that I did here. So this is invariance. Everything invariance. This is order. It's well, you say lexicographic order for this. It's also fixed. When I apply diffeomorphism, the order will be not fixed. So if I take what is the Gröbner basis in this ideal, because okay, and if I say that this basis should be reduced, it means that higher terms should have coefficients equal 1. So if it's reduced, then there is theorem that reduced basis is unique. Okay, now it means that our diffeomorphism will be transform this polynomials itself. It means that, but this is, guys, they will not change it under this transformation. So it means that our diffeomorphism will be acts on only on coefficients of these polynomials. And because this everything invariant, so these coefficients have to be invariant. So it means that taking invariance of our linear operator, this I, applies the derivations, take this polynomial ideal of polynomial relations between them, and take basis, the reduced basis. We take coefficients of the reduced basis, we will get invariance of our operators.
I missed something because the idea was to get rid of derivatives of this
F.
and
It's this components.
yeah. And
so, but invariants that I will get, they just also rationals in
Yes.
coefficients also.
Yes.
But the field of such functions has transcendence equal dimension of this bundle.
yes.
What it means? That it means that if I take this number of this invariance bigger than this
You
dimension,
can get rid.
I will get polynomial relation between them.
Yes.
So, and this is just will be polynomials that I will put inside of my ideal.
Mm-hmm.
After this, this ideal will be in this algebra of polynomials. So what I see that the diffeomorphism acts in invariant way on this polynomial. So they preserve ideals, they preserve this xn, they preserve order.
If n is big enough, then
Yeah,
you will find
right.
we need a
Yeah, really, what we need that n will be big than dimension of this is pm0, pl0, and something like this.
Yes.
So if you take enough derivatives, then you can just simply rid of these components.
Yes.
And then therefore you will get simple invariance. Okay, now about it's the same really. You remember that for if we have this invariance for our operator, then you remember how to get it. You have this operator, then apply this universal operator to degrees of this invariance. You will get really the set of the invariance that will generate all other invariants. So exactly the same situation here. Because once more we have universal operator, but now in these bundles, in these ones, and then you also will find some invariant. Then you will apply this new operator, say that delta number to the degrees of this invariance, and you will get really the complete set of differential invariants. And once more, they uniquely described this operator. And therefore the nonlinear operator.
But to get explicit expressions is quite difficult.
For small dimensions, no. For small dimension, at least it's easy to write soft for all these computations, but say this it's easy to say, but to find this is by Gröbner basis for some ideal. Yeah, certainly it's easy to say, but not at least my computer stop it in very simple situations. So but I think it can be just change it a little, but at least what I wanted to show that really this way give you some number of invariants, and this is invariants generate all natural invariants for this type of nonlinear operators. Okay, maybe now a few years I will not disturb you by these invariants. We have really more interesting problems.
Well, thanks a lot. Well, when our speaker is washing his. No, okay. Questions, remarks? Are you still alive? Okay, no questions, no remarks. So thanks a lot. Next time we have a short workshop dedicated to the 60th birthday of Maxim Pavlov, and then the last session. Next Wednesday, yeah. Okay, and then the last session on 21st of December. Goodbye. Thanks a lot.